Hey, I'm Colin White, and I'll be presenting our paper on encodings for neural architecture search, which is joint work with Willie Neiswanger, Sam Nolen, and Yash Savani. In the last several years, deep learning algorithms have been getting increasingly more specialized and complex. The figure here is the popular DenseNet architecture from 2016, which was designed for the ImageNet dataset. However, it's obviously time-consuming to create a specialized architecture like this for every use case. So in the last few years, there's been a very popular area of research called neural architecture search, which seeks to automate the process of finding the best neural network for a given dataset. There are many techniques for NAS, including Bayesian optimization, evolutionary algorithms, and one-shot differentiable methods. The majority of NAS papers today conduct the architecture search over a cell-based search space consisting of hundreds of thousands of architectures represented by directed acyclic graphs, such as the examples on the bottom. Each node or edge represents an operation, and the paths represent the flow of data through the neural network. In order for NAS algorithms to search over a DAG-based search space, we need a way to encode the architecture. The simplest and most common way to do this is by constructing the adjacency matrix corresponding to the DAG, as we see on the right here. The study of the encoding as a design choice in NAS has been largely neglected. Only recently, two papers tried a different encoding and showed that it can have a large effect on the performance of NAS algorithms. In this work, we give the first formal study on encodings for NAS. In the rest of the talk, I'll define 8 different encodings, talk about our experiments based on NAS subroutines, and then discuss the scalability of each encoding, as well as a few more experiments. My goal will be to convince you that encodings are an important design decision for NAS. Okay, so first we formally define an encoding as a fixed multifunction from a DAG to a real-valued tensor. Note that this doesn't include trainable encodings like graph neural networks or variational autoencoders, since the function depends on the dataset, so we consider those to be part of the algorithm itself. But we do still compare to those in our experiments. We define 2 paradigms of encodings: adjacency matrix encodings, as discussed earlier, and path-based encodings defined by White et al. In 2019. The one-hot adjacency encoding is similar to the is simply the adjacency matrix together with a list of operations at each node. The categorical version is similar, but we use indices of the matrix entries, which are 1. There's also a continuous version of the one-hot encoding defined by Jung et al. 2019, which is very similar, except the entries can be any number between 0 and 1, and we're also given a threshold. A downside of the adjacency matrix encoding is that there's an arbitrary node ordering, and also the features are highly dependent on one another. For the path-based encodings, each feature represents a possible path from the input to the output. For example, on the left here, we could have input, max pooling, 1-by-1 convolution, and output. For each architecture, we compute all the paths from the input to the output and set those features to 1. In this example, there are 364 total possible paths, and this DAG here has 4 of them. The path encoding also has one-hot, categorical, and continuous variants, just like the adjacency matrix-based encodings. We also define truncated variants of the path encoding, where we shorten the path encoding by truncating the paths which are least likely to occur. For instance, the really long paths. We note that the path-based encodings are not one-to-one functions because multiple DAGs can map to the same encoding, as we see on the left here. Similarly, for the adjacency matrix-based encodings, the inverse functions are not one-to-one, because multiple matrices can map to the same DAG. Because of this difference, many prior NAS algorithms unknowingly use encodings that are not compatible with other NAS algorithms. Therefore, in order to experimentally compare these encodings, we must go to the subroutine level. We identify 3 subroutines: sample random architecture, perturb architecture, and train predictor model. These are the only encoding-dependent building blocks necessary for many NAS algorithms, as we show here. Now, for each subroutine, we identify a couple of NAS algorithms which heavily make use of that subroutine, and then run an experiment trying out different encodings for that subroutine. For the perturb architecture subroutine, Regularized evolution and local search make heavy use of perturbing architectures. We run experiments on NASBench 101 and 201, and we find that the adjacency matrix encoding works best here. It is often the case that some encodings are functionally equivalent to one another in certain NAS algorithms, which is why we don't have the full 8 encodings listed on each of these plots. Next, we study the random architecture subroutine. Most NAS algorithms start by drawing a few architectures at random, and this is typically instantiated by drawing components of the encoding at random. Each encoding defines a different distribution of architectures. We've found that, again, the adjacency matrix encoding works best here, both in random search and at the start of other NAS algorithms. The distribution defined by this encoding works even better than the uniform distribution. Finally, we study trained predictor model, i.e. using a surrogate such as a Gaussian process or a neural network to predict the performance of untrained architectures. For a neural predictor, we found that the path encoding significantly outperforms the adjacency matrix-based encodings. Even in follow-up experiments against graph neural networks and variational autoencoders, the path encoding still came out on top, with the graph neural network getting second-best performance. Overall, our experiments act as recommendations for what encodings to use in NAS subroutines for future work. Now I'll briefly mention the rest of our results. Earlier, I mentioned that the path-based encodings are not one-to-one functions, which is a downside because multiple architectures map to the same encoding. However, we showed that this may actually be a benefit since architectures with the same encoding tend to have quite similar accuracies. On the right here, we plotted the amount of truncation of the path encoding against the average standard deviation among architectures with the same path encoding. So this value is close to 0 for the full-length path encoding on the rightmost part of this plot, especially compared to the leftmost part of the plot, which is just the standard deviation of accuracies for all architectures in the search space. So basically, even though the path encoding is not one-to-one, which means we can't differentiate the architectures sometimes, it's a good thing since our goal is just to differentiate the architectures based on their accuracies, and that's not a problem here. Okay, so next we theoretically and empirically show that the path-based encodings scale better than the adjacency matrix-based encodings. The full-length path encoding is exponential in the number of nodes, while the adjacency matrix encoding is quadratic. So it might seem like that the path encoding would perform badly on large search spaces, since it doesn't scale nearly as well as the adjacency matrix encoding. However, we're able to theoretically characterize the loss of information when truncating the path encoding as a function of the number of nodes and edges. We find that when the number of edges scales quasi-linearly with the number of nodes, then truncating the path encoding to be linear results in negligible loss of information. Furthermore, we showed that the same does not hold for the adjacency matrix encoding, which cannot be truncated at all. This means that the path encoding can effectively be shorter than the adjacency matrix encoding. Our experiments verified this. As you can see on the left or on the right, the path encoding in orange can be truncated much more than the adjacency matrix encoding while maintaining its performance. And finally, we tested the ability of the neural predictor with each encoding to generalize beyond the search space on which it was trained. We ran this experiment on NASBench 101 by training neural predictors on a subset of the search space where each architecture has a constrained number of nodes and edges, and testing on the rest of the architectures. We found that the adjacency matrix encoding performed the best because for the path encoding, there are paths and architectures from the test set that don't exist in the training set. But this is not the case for the adjacency matrix encoding. Okay, so overall, we find that encodings are an important design decision for NAS, and we also give recommendations for what encoding to use for which NAS subroutine for future work. Please see our poster or paper, or go to this GitHub repository for more information. Thank you.